in your pocket, or
Next up will be Kelton Halbert talking about simulation analysis of severe thunderstorms on deep waters.
I'll give you a heads up when we're ready.
All right.
Very good. Go ahead.
So yeah, my name is Kelton Halbert. I'm from the University of Wisconsin-Madison, working in the Cooperative Institute for Meteorological Satellite Studies, which I don't do anything satellite related, so it's a fun thing. But I'm here on behalf of my advisor and PI, Dr. Leigh Orf, to talk about what we use Blue Waters for, and that's simulating violent, long-lived tornadoes using numerical models, and have some new and interesting stuff to show from that over the last couple months, actually. But first off, just the problem of what we're trying to use Blue Waters to solve is that supercell thunderstorms tend to be responsible for the strongest and deadliest tornadoes in the EF4 to EF5 damage rating range, which again are responsible for the largest losses to life and property. But we don't fully understand why these storms develop, as there are only a small subset of all tornadoes, and even at that, all supercells. Only 1% of tornadoes are classified as violent, and of that, only a quarter of supercells approximately produce tornadoes. So it's a very difficult prediction problem, and made even worse by the fact that we actually don't even understand the dynamics that lead to tornado formation in general, much less the deadliest, most costly ones. On top of that, collecting observations from supercells and tornadoes is incredibly challenging, often very dangerous, and the resolution, either spatially or temporally, can often be too coarse to get at some of the underlying processes that lead to tornado genesis and maintenance. And so that's where the numerical modeling comes in, is that by using the full set of fluid dynamic equations and providing sufficient resolution, that we could maybe get at the processes in these deadly tornadoes and maybe start to distinguish them from the not so deadly tornadoes and lead to better prediction. So kind of going off some of that again, the reason why people care about this is right now the tornado warning false alarm rate is about 70% for the National Weather Service, and that's been steadily decreasing over the last several decades, but that's still a high false alarm rate if you want people to actually take you pretty seriously. And on top of that, there are still rare situations in which tornadoes occur without warning. This is much less the case these days, but it can still happen and still can be even a deadly or violent tornado with no warning. And we want to eliminate that, give people as much heads up as possible. Again, more fatalities in the rarer events, and so people care about that. And despite the advances in numerical modeling and operational meteorology, we weren't really able to get the resolution required to get at some of these processes until Blue Waters. And that's what my advisor started doing when the first allocation in 2013 was to start working on these problems. And so to do these simulations, we've kind of had to, in conjunction with some of the Blue Water staff, come up with some creative ways to handle things like the data load. We realized that with wanting to save these high-resolution data sets, both temporally and spatially, we didn't need the full range of 32-bit or 64-bit precision, so we used the ZFP plugin for HDF5 to provide an accuracy parameter that then for each array, and we can decide how much of one thing we want to compress and save versus another. And that's really allowed us to actually run these things at scale and save the data and do proper analysis. On top of the data storage was the model I/O problem. So Leigh had to rewrite the entire model's I/O core to effectively work as a distributed file system. He calls LOFS, or lack of file system. And it's just a bunch of HDF5 tiles that are self-describing that can then be reconstructed on request after the fact. And that means that when the model's running, it's spending less time communicating arrays to MPI and allows it to just write and move on to the next step. In order to save space, we only save the bare minimum fields, which means that we use a lot of GPU code to recompute necessary variables post hoc. And same thing, we've started to develop trajectory, Lagrangian trajectory code on the GPUs on Blue Waters that will allow us to do more complex quantitative analysis with some of that stuff. So these are just some of the challenges we've had to go through, and beyond just running the simulation and actually taking advantage of Blue Waters to its fullest. So previous work that some of you might be familiar with from previous years was Leigh's process was kind of setting up the model. In 2013, there was a successful simulation of an EF5 tornado at 30-meter resolution. This has kind of been our control run that we've been working on since I started at Madison 2 years ago. That data set's about 67 terabytes, contains 32,400 time saved every model time step, which is 1/6 of a second, throughout the entire life of the tornado. So we've basically saved the entire simulation in amber so that we can do all the visualization and analysis we want without having to rerun on the nodes. And it's kind of nice that way, and that's where the GPUs are super helpful. We've also done simulations of the same environment at 20 and 15 meters, and then some new simulations of different supercell environments that have produced other violent tornadoes in some different storm structures. So we're starting to see some patterns in other atmospheric environments that show these things might actually be real, and starting to uncover that. And so to the fun stuff with the animations, this is a sequence put together by David Bach at NCSA. It's one of my favorites because when people ask what I do, I just kind of show them this and go, that's essentially it. But in more detail, the simulation is essentially initialized from a virtual weather balloon profile that gives us temperature, dew point, pressure, and the winds. And we put that in a horizontally homogeneous base state in the model, and we perturb it with a little updraft, and we say run. And so this is what the model ends up doing, is it grows a thunderstorm in that environment, and then we essentially hope and pray that it produces a tornado. We actually don't know going into it whether or not you get something that looks as good as that, or if the whole thing kind of just blows up into a convective mess, or if it's a supercell without a tornado. It's very random. That's the process of how we grow it. And then through these simulations on Blue Waters, we've identified some new features previously not talked about within the sciences. This is something we call the streamwise vorticity current that we believe to be very important for either both tornadogenesis or maintaining strong, long-lived tornadoes. And it's actually a feature that has motivated several field projects. There's actually one ongoing right now based on this work to go and hunt for these features in supercell thunderstorms. And talking to a couple colleagues, they've actually managed to find them in reality. It all started with some Blue Water simulations. This is just another view of a similar thing with the vorticity field, or the amount of spin and rotation. And again, just picking up on the fact that there are these really small, fine-scale features that seem to be important that we just miss if we look at things in the traditional observation networks with radars, or even the 100-meter simulations of previous studies that deemed those to be sufficient resolution. We're finding that there's even smaller scale features that are important. A lot of what we do is also comparing them to observations. And so this is something put together by a storm videographer named Hank Scheima from Houston, and essentially putting side by side the simulations with the real atmosphere. Is the model actually showing us things that we know to be true? So when you've got something this high resolution, you're seeing features that haven't been seen before, you've got to look for other cues that tell you, okay, this is physical or representing real life. I always enjoy looking at this sequence because it really points out how many of the flow features seem to be matching the real atmosphere, and showing that we're probably on the right track with some of these things. And again, it's motivating others in the field to start looking for some of these important features. And it's pretty exciting because of that, and seeing other people find things that you've only seen in a computer. But with that said, I think this is the end of the sequence here, but this was our 30-meter simulation run, which we can now have managed to get scaling on Blue Waters well enough that we can do these pretty routinely. I think we can chug one of these out per day if we wanted to, or maybe it's 2 days, but pretty quickly. Doesn't use that many nodes. The exciting stuff right now is within the last couple months, Dr. Orf has really kicked things up to 11 with the simulation, and so we're working on a new hero simulation at 10-meter resolution, completely isotropic throughout the whole domain, about 250 billion grid points, 1/20th of a second model time step, and a single restart checkpoint was weighing about 35 terabytes on the disk. So turning on some compression, we were able to make the run go further out and save more of the data that way. But we can't use any lossy compression with the restart checkpoints. We started running it in April. We're only about out to 6,000 seconds of the simulation. I'm not sure how far Leigh wants to go with it, but we do finally have an EF5 tornado at this 10-meter resolution. And because of the challenges of the previous simulation that we've kind of worked to overcome, this is more than just kind of a one-and-done visualization. Can we do it? It's actually going to be saved and analyzed at scale as well, which is really exciting. So here's some of the animations from this. Literally just got sent to me yesterday by my advisor. Some really exciting stuff with the 10-meter simulation, but this is the vertical vorticity painted on the swaths at the lowest model level. And we can see these really unique features where we're seeing that the tornado genesis and maintenance is kind of more of an aggregation of vortices from all over, and we're starting to see smaller sub-vortex features that match what we see in reality with the damage paths and swaths. And these were flow features that we weren't able to capture in the 30-meter simulation due to the resolution. So now these are actually the sub-tornadic vortices, and again, you can see it in the horizontal wind speed maximum that southern side is kind of being dug out, similar to that photo from the EF4 tornado in Illinois. This one's just showing the pressure minima along the track. So again, we're getting these individual subsuction vortices within the tornado, and that's really important because these multiple vortex tornadoes that have these small suction vortices can actually have translation velocities that are near 200 miles per hour, not including the rotational component. So understanding the dynamics of those is of great interest to the community there. A similar video, but with our buoyancy field, essentially, or whether or not the air is rain-cooled or from the warm inflow. And even at 10 meters, we see a similar result to some of our previous 30-meter work, and that most of the air that feeds the tornado actually comes from the rain-cooled downdraft air, which is something that is pretty interesting. That seems like all the vorticity that feeds it comes from out there as well. Let's see if I can jump ahead a little bit for the sake of time. Cloud field of the simulation at 10 meters, again, just kind of showing the structure of the tornado. It looks pretty realistic. It's kind of mind-blowing to think about that this is a simulation and not real life. Sometimes I did some storm chasing in undergrad, and it looks just about as real of a tornado as any I've seen. And again, just getting those really small, fine tornadic structures is really exciting because nobody's been able to do this with the whole paired supercell involved in the simulation. Again, just from a different view, I think there's a comparison to that same Fairdale, Illinois tornado from that had the swaths in the earlier thing. Yeah, there it is. So again, just making sure that we're capturing the right flow features, and it's doing pretty good. So this is officially the highest resolution simulation of a supercell and tornado ever conducted to date. It's still going right now. So if you see the queue fill up with about 3/4 of the XE nodes, I apologize. It's probably us. Yeah, so this is just the, again, the vertical vorticity field showing, or volume rendered painted with the magnitude on the surface, just showing we're getting these individual suction vortices within the tornado, which is something that's very new to these simulations for us. Just let that run for a moment as well. And yeah, so just some parting thoughts. Blue Waters has enabled breakthrough science in supercell and tornado modeling. As of now, the 10-meter simulation is the highest resolution study of a supercell and tornado ever conducted. It's still ongoing. I don't have much to say about scientific results of it because of that, but it seems like we have convergence of solutions between our 30-meter and our 10-meter run, which is good. And we have a couple of questions we want to address between the two simulations. But the Blue Water staff was instrumental in getting things like the ZFP compression compiled and set up, handling node failures and reservations with this simulation. I know Leigh's been super thankful for how responsive people have been on the Blue Water staff whenever a node goes down or the simulation hangs or the IO hangs. And then it'll continue to be instrumental as we continue to run this data set and then hopefully move it off quickly enough and can then continue to do analysis further on. And just throwing up the acknowledgement slide for all the collaborators and the NSF grants that support this work. And thank you to Leigh for having a talk in Canada so I get to enjoy the beautiful weather in Oregon. And with that, I'll take any questions. You do that by trying to relate it back to something from the environment that produced it, or the signals and trends in the simulation from things like simulated radar. So something a colleague of mine, a fellow graduate student Austin Dixon, is doing is he's set up sort of a radar emulator in the simulation and focusing at these features to be able to say these are what these things look like to the mobile radar fleets that go out and research these things and the operational Doppler radars that the Weather Service see. And so the idea is you kind of try and relate it back to that stuff, or you relate it back to the input data that generates the storm. But yeah, it absolutely is a challenge. And I don't think people will be running simulations like this operationally soon unless it's going to be some sort of ensemble approach to seeing, does this environment produce, out of the 10, do 5 produce tornadoes or something like that? Maybe this could have that approach, but it is a challenge.
So, great presentation, really great visuals. I had a question. So, do you see the possibility of using all of the simulation data, especially when you notice that your simulations develop such closely granular features as compared to real tornadoes? Do you think you could possibly feed all the data in the future to machine learning algorithms that would eventually help you predict real time?
Yeah, so we're definitely looking for ways that we can apply it to machine learning. Most of that, the lack of effort in the area has come down to mine and Leigh's inexperience with AI. My understanding is it works really well with classifying things, and so we have yet to determine any sort of experiment where we can label and have it classify and say, look for this feature. So I would say at some point, probably, but we don't quite know what it is we would train it to look for just yet. But there's possibly a scenario in which we could teach machine learning to look at a set of input profiles and say, pick the one that's most likely to produce this expected result. And there might be something there, but that's totally dependent on whether or not the math checks out that there really is a relationship between the larger scale environment and the tornado.
So you mentioned that when you run your simulations, you grant hope that tornado appears. So I'm really sorry for the question that I'm going to ask, but essentially 2 questions.
Mm-hmm.
First of all, have you ever witnessed, let's say, the death of a tornado in your simulations? And if you have, or either way actually, do you think mankind can design anything to make it go away?
So the answer to the first question is yes. It's really easy to get a simulation with a weak tornado that's short-lived and no tornado at all, tornado that dies quickly. Those are kind of the everyday simulations that show up. So that's why we focus on the longer-lived one, longer track one, because that represents a space that we don't understand a whole lot about. But as far as finding ways to geoengineer a way out of tornadoes, there is, to my knowledge, isn't really anything that's super helpful there. I know some people that have actually tried cloud modeling studies like this and did hypothetical, how much dry ice would it take to kill the updraft and stuff. And it's just, the numbers are massive in what you actually need to disrupt the flow and the amount of energy that's going through the system. So I don't think that's something that's going to be revealed through the simulations.
As far as the streamwise vorticity that you mentioned goes, is that closely analogous to helicity then?
Yes, so streamwise vorticity is essentially helicity. It's the wind parallel component of the vorticity vector, which I'm pretty sure is the definition of helicity, if I don't remember correctly. Someone else asked me that same thing, and it tripped me up because of verbiage, so I'm pretty sure that's correct, yes. Yeah, so it's just the helical flow.
So you mentioned that when you go from the 30 meter to the 10 meter, you are seeing some improvement on kind of some of the features. But I was wondering if you guys have quantified the differences between, say, like 30 and 10 by maybe to the 10 still running, or like the 50 meter and the 30 meter, to see like how much better it is to keep scaling this to higher resolution.
Yeah, so we haven't really done any sensitivity studies in like how fine do you have to get. I mean, so our coarsest resolution simulations are around 50 to 100 meters and show similar features on the large scale. So if you were looking for a minimum, you probably don't need to go much finer scale. But if you're really interested in capturing the internal tornado dynamics, as well as making sure that turbulence closure truly is dissipative in the large eddy simulation, that's where going to the smaller resolution is better. But I mean, the only differences we've really seen so far in the 30 meter and the 10 meter when it comes to the resolution is just the timing everything happens at. Because the boundary conditions are free slip. They're a form of free slip that have lots of strain gradient. I won't go too much into that, but basically I think we're seeing that the smaller resolution you get, the longer things take to spin up and spin down because it's free slip. But aside from that, I haven't noticed anything too drastically different. But you wouldn't necessarily want to run at 10 meters unless you were wanting to get the subtornadic vortex structure.
How much do you think droplets and debris would matter in the sustaining or forming?
Yeah, so with the tornado itself, we're definitely at the scale where if you wanted to be as close to reality as possible, the drag induced by debris on the tornadic circulation, I think, would be of order of importance here. But I don't know that it really has as much of an impact on the dynamics of how it's formed or maintained, only because those seem to be driven by the low-level updraft in the thunderstorm itself, and those wouldn't be as impacted by the debris. But I do know things like even the water, there's a water droplet breakup parameter in the cloud microphysics scheme, and if you change that even a little bit, you'll get some very different downdraft cold pool temperatures. So the way you handle all that stuff is important, but I think the debris stuff is really only important around the tornado itself. And there are some people that have developed debris models for this kind of thing that we could try, but we don't necessarily think it's as important for the science questions about the supercell itself.
Is there a technology barrier that would help you to advance your research?
If I could snap my fingers and wish for one thing, it would be the model that we have right now made for GPU. And it's something that has been tossed around a lot, but I've told my advisor I'm not going to do till my PhD is over because I'd like to graduate and not write a numerical model from scratch on the GPU. But I think that for us, the technology is already there, and we see the possibilities with how scalable GPUs are, especially with the NVLink memory bandwidth, and seeing the trend in supercomputers, like with the new stuff at Oak Ridge. I can't remember the name of the computer, but that's the direction we see things going. And so I would like to have the code already working on it, but that's why we're trying to build all these GPU tools, is to kind of work our way there.
One last question. All right, join me in thanking Kelton.
Thank you.